Hello. The title of the talk is Making Sense of BGP. This work is done in collaboration with Van Jacobson and Cengiz Elitunogo at Packet Design. This is an overview of the talk. We've developed two techniques to help diagnose BGP problems. The first technique is a visualization technique called TAMP, which helps you visualize a set of BGP routes. And the second technique is an analysis technique called stemming that helps you do root cause analysis. Both of these techniques are driven purely by BGP events. They don't have any built-in models, statistical or otherwise. And what we're doing here is to see the world as the routers see it. We're not trying to map the whole internet like some other research are doing, which is great work. But what this is a routing diagnostic tool. This is an architecture of how the two techniques fit together. On the top is TAMP, the visualization technique. TAMP takes a BGP event stream or a subset of BGP event stream and can spit out a static picture. It can also track the events and spit out a dynamic picture, an animation. At the bottom is the analysis technique, stemming. What it does is a root cause analysis, and it can spit out a one-line diagnosis or also a future set of the events to fit into the visualization technique. And this is the only coupling between the two parts. So these techniques can be used separately or together. We'll first go over the static version of TAMP. TAMP stands for threshold and merge prefixes. Now, this is how it works. For a particular BGP peer and a specific time, that peer's route from a tree at the root, from a tree rooted at that peer. So what the tree look like is the BGP peer as the root, the BGP next hops, the next hop AS, and then the rest of the AS. We assign a weight to the edge in the tree as the number of unique prefixes that edge carries. Because we are interested in the edges, the part of the tree that carries most of the prefixes that are heavily used. Now what we get would be a pretty bushy tree, just how BGP routing works. So what we want to do is prune all the edges that have weight below a certain threshold. What we get then is a subtree of the original tree, but still rooted at the same peer. Now we construct this subtree for each BGP peer you're interested in, and then combine the subtrees together. By combining, we can't just add the edge weights together simply, because the edge actually carries the edge weight is the number of unique prefixes. So what we have to do is to keep the set of prefixes on the edge and essentially do a union of these sets and take the size of the union as the new edge weight. Now, TAMP can map any prefix, any set of routes, and by picking different sets, it can validate what you think your BGP routing looks like or can help diagnose some problems. Here is a case study at Berkeley. Now what you see here is essentially Berkeley's overall view of what BGP looks like, how they see the outside world. At the far left is Berkeley campus, and the two nodes you see right next to the square box are the BGP peers. Next to them are the BGP next hops exported by those peers. And then the rest is the AS tree. The thickness of the edge is proportional to the number of prefixes that edge carries. Now, most of this picture is really not surprising what you're expecting. Berkeley only has one provider at that time, CARAN, so all the prefixes go through CARAN, and about 80% of that goes through Quest, and then you see the usual suspect of tier ones, level 3, AT&T, and so on. And Berkeley also have about 6% of the prefixes coming from Abilene. Now, but actually part of this picture is not expected even to Berkeley. Let me give you some context. At the top router, the top BGP router, the one that says peer with policy, is the path that carries the commodity internet routes. And they have 2 BGP next hops for low balancing, and they are rate limiters. And what Berkeley NetOp was doing is just simply splitting the prefix space in half, and they think they're splitting it exactly in half and low balancing it onto 2 next hop. But what this picture shows you is, no, that's not what's happening, and most of it is going through one of the next hop. Now this picture maps all the prefixes, the overall view of what Berkeley sees. But TAM can map any subset of routes, and one meaningful subset is BGP communities. Now, a lot of BGP policies are tied to BGP communities. For example, route preference, filtering, setting route scope. So because so many things are actually relying on BGP communities working, it's useful to see what those communities really mean. Do they really mean what the documentation says it means? Now here is a visualization of a scenic community that scenic says is tagged onto routes coming from Los Netos. Now we do see about 30% of the prefixes do come from Los Netos, but more than twice of that actually comes from KDDI, which is a Japanese ISP. So why is KDDI there? If Berkeley is using this community to give special treatment to Los Netos, then this community won't be working correctly for them, because they will be also giving special treatment to KDDI, things coming from KDDI, from Hong Kong, from Korea, and from Japan. Now, a static picture is useful, but often it's not sufficient, because routing is fluid and it changes all the time. Now, TAM can map any set of routes, but it doesn't really, it can't say these are the important things I will look at. It doesn't tell you which are the routes that it should map, and that's how the analysis part comes in, stemming. What stemming does is it picks the right set of events and the prefixes in them, and it can let you visualize them, or it can spit out a one-line diagnosis. But this kind of analysis, a root cause analysis, is a really hard problem. Why? Because BGP is extremely chatty. This is an event over time graph. So the y-axis is number of events, and the x-axis is time. And this is at Berkeley sometime last year. Now, you see a couple of event spikes, and the largest event spike has about 1 million events. So what happened there? I mean, is it something that Berkeley NetOp has to look into, or is it somewhere far away? Can it, Berkeley ignore it, or does it have to take action? Now let's look at this, some of the events from one of the event spike. This is a very tiny portion of one of the event spike. There are probably another 30,000 pages that you have to look at. And after this page, I'm already sick of it. I don't want to look at more events. But BGP sent you 1 million events, not because 1 million things happen. That's because BGP can only talk at the prefix level. Probably a few things happen. Appearing lost, some bunch of prefixes got policy change and moved somewhere else. But there's no way for the protocol to tell you that 1 or 2 things that happen. It can only tell you 1 or 2 things happen in 1 million slightly different ways. Now, let's just take a bunch of events from that event stream and a bunch of withdrawals and look at what they look like. Now you see, actually, most of the withdrawals from that event spike has 11423 and 209 in the AS path. So 11423 is Karen and 209 is Quest. And you see the BGP router IP address and the next hop. But why do they have this common portion? And that's because somewhere in the original routing tree, a failure happened, a branch was cut. And this common portion we call a stem, thereby stemming analysis, actually tells you where that failure happens. The failure happens at the last edge of the common portion. In this case, it's between Karen and Quest, 11423 and 209. Now, if the cut actually happens one hop down between Quest and AT&T, then that common portion will include AT&T as well. And the failure would be the last edge of the common portion, the stem, which is between Quest and AT&T. Now, this concept of finding the common portion is very intuitive, but actually it's not a trivial problem. Finding the stem itself is actually has some complicating features. We can't just do a simple correlation. Let's just correlate all the events and see what the biggest correlation is, because all events would be correlated at the root. Everything would come from the beginning of the AS path. Like in this example, everything would be coming from Berkeley. And one other thing that is complicating is the way the internet works. Probably multiple things always happen at the same time. And what the analysis have to do is to first find all the things and pick out the different things happening at different places and put them apart. We can't confuse them as one thing happening. So in this example, if there's a failure between Karen and Quest, and there's a failure between Karen and Evelyn, then they should be two separate incidents. Now, actually, this kind of correlation analysis is well established and common field in statistics, and they're usually solved by algorithms like principal component analysis, hierarchical clustering, and so on. What these algorithms do is to rank the correlations from the biggest to the weakest, and you'll find all the correlations. But in our context, in the context of BGP, using these algorithms is computationally very expensive. They're usually on the order of n squared, or with much implementation complication, order n log n. And in our case, n is pretty big. It's not the number of AS. It's actually not the number of AS paths. It's actually the number of AF path stems, all possible AF path stems. So, well, that's not good, because we want a practical operational tool. We don't want to wait for hours before knowing what happened. But that's okay. There are certain BGP path structures that we can exploit in the algorithm. So what we did is develop a linear time algorithm called stemming that exploits such path structures. And this algorithm runs real time on a modern processor. Now, so far we have used examples from Berkeley, which has a pretty simple topology, a tree-like topology. They only have one provider, Karen, and it splits out from there, and they only have like 4 BGP speaking routers. But this algorithm also works on more complex forest-like topologies, like the ones you find at tier 1s, which can have hundreds of BGP routers, BGP peers, thousands of BGP next hops, peering with most of the or all of the other tier 1s, and then hundreds of customers. So how well does the stemming analysis work? I mean, what kind of stuff does it find? I mean, what can it show you? Now let's look at this case study. We will show what happened in that one event spike. Now what we are trying to show here is not part of the analysis. What we're showing here is we have stemming, the analysis technique, pick out what happened in that event spike and pick out the subset of events responsible for that incident, and we feed that subset of events to TAMP, the visualization technique, and we visualize what happened. So visualization is not part of the analysis. So let me explain this picture a little bit. Okay. So the top half of the graph is similar to what you saw. You see Berkeley campus, Berkeley BGP peers, the next hop, and the AS. On the bottom, we have a couple of new legends. In the middle is a prefix versus time chart for a particular AS edge. In this case, it's between Karen and Quest. And on the left is a time, a clock that shows you the seconds, minutes, and seconds into the event stream. And one other thing, if an edge is blue, that means it's losing prefixes on the edge. If the edge is green, it means it's gaining prefixes. If it's black, that means it's not changing. So let's play this visualization and see what is happening. So what is essentially happening, which you can also see in the time series chart, is between Karen and Quest, they lost about 30,000 prefixes. Now, what is really surprising to us and also to Berkeley is when that happens, let's move back time a little bit, is the top path, the one that is, has higher precedence, that carry commodity internet routes, and has the rate limiters, also stop announcing all those 30,000 prefixes. But we know there is a backup path because the bottom lower precedence router pick up the backup path right away. So essentially what happened there is all of the traffic went through the lower, more expensive, not rate limited path. And we looked through the communities because Berkeley heavily utilized communities. And what happened is when the failover happened, Karen didn't tag the right communities onto the backup path, even though at the end it does come from an ISP route. So which is the second observation. Look at this tremendously, unbelievably long backup path. It went through Karen South, Packet Clearinghouse, Alpha Nab, San Diego Supercomputing Center, Scenic, and then Level 3. Now, the power of the analysis of stemming is it picked out the 1-hop original path and the 6-7 hop failure path. And the power of the visualization is, let me move back in time. As we see the failover happening, the visualization actually shows you the intermediate states. You see routes originally coming from AT&T through Quest and from Sprint through Quest, now move from AT&T to Level 3 and Sprint to Level 3 to this long backup path. Okay. So, yeah, picking out a peering loss like this is nice, but, well, can it find other stuff? Can the analysis find other non-spiky incidents? A lot of serious problems actually don't manifest the result in distinctive event spikes like route oscillations. So can stemming the analysis help here? Yes, it does help. Stemming is not just about finding and explaining event spike. Now this is because one of the most important property of stemming is temporal independence. It does not depend on the sequence of the events. It doesn't depend on the time range that you select. It doesn't have time in it. And it works like that because the concept of correlation is well defined at any time scale. So for example, if you have a peering loss, the time scale would be in the order of convergence, a small time scale. And the biggest correlation would come from the massive prefix announcement and withdrawals. But if you look at a longer time scale, like days or hours, days or weeks, and there's a route oscillation happening, that the biggest correlation would come from the continuous oscillation, because that biggest correlation would overwhelm the other correlation. So let's look at a case study. This is a BGP event rate graph, same as before. Y-axis is number of events and x-axis is time at a tier 1 ISP in the US sometime in 2002. Now you see a couple of event spikes in this picture, but actually the most serious problem in this picture is not in any of the event spikes. It actually disguised itself as low-grade BGP churn in the yellow box. And you wouldn't think that's happening. So what the problem is a persistent route flap about once a minute, and it involved a customer, and it lasted about a month and a half. And this is what it looks like. So let me explain the setup a little bit. It's a relatively common setup. The customer has a direct peering with the tier 1, and it also have connection with a NAP. So it has a single one-hop direct path to this tier 1 and a bunch of free-hop indirect paths through the NAP, through other tier 1s, through this tier 1. Now what is happening is this direct path between the customer and this tier 1 is flapping, and it flaps about every minute, going up and down and up and down. And when it goes down, all the other POPs in that tier 1 say, well, I have an alternate path that goes through other tier 1 and this NAP. So they start announcing these alternate paths. And when the customer paths come back up, like right now, well, it's going down again, the other POPs will withdraw their alternate paths, and this went on about a month and a half. Now, I want to also go over one other thing here. When the other POPs are announcing the 3-hop paths, you see a whole bunch of paths now coming up, but then some are made to one tier 1 and then broken and moved to another tier 1, and this is a preference working. So at a time like this, you can use the visualization tool to validate whether your preference is working the way you're working. Is it really going to one place that I think that it should be going to or not? Okay, so I want to show you another oscillation. At the last NANOG, Danny McPherson talked about mad oscillation and how bad they are, and we don't want them. And stemming helps you find such oscillation. And here's one that happened at a tier 1 ISP in the US. I'll just play it for you. What is happening is, let me explain this graph. The bottom two routers called 2, A and B, they belong in the same POP. And the top two, called 1 A and B, they belong into another POP. The bottom two BGP peers somehow went crazy, and they were announcing and withdrawing the same exact route every 10 microseconds. And that's every 10 microseconds. You don't think BGP can speak so fast, but it was doing this. So that's why it's yellow, because we don't want to show blue and green just, flapping like every 10 microseconds. And that actually drives the classical MET oscillation setup described by RFC 3345, and drives the upper two routers in the same pop just going up and down. So this only involves one prefix, but when it was happening, it accounted for 95% of the total BGP events. That means that it inflated the BGP traffic by a factor of 20. Okay, so we show a couple of visualizations of the results from stemming, and that it works accurately. But the main point of the techniques is not really in the visualization. Finding the incident, the failure that happened, is a lot more valuable than visualizing it. So if there's one point to take away from this talk, is the analysis technique can crunch down 1 million events and spit out a one-line or two-line diagnosis in this case. So this is the output of stemming, the one-line diagnosis I've been telling you about throughout the talk. So at certain time, this BGP router lost 28 to 93 prefixes, and the peering fell from Carol and Quest to this long backup path. About 20 minutes later, it gained back those 30,000 prefixes, this peering Karen Quest through Karen and Quest peering restore. So that's the kind of the main point of the analysis. Okay, last but not least, I want to thank UC Berkeley NetOp, and especially Ken Lindahl for allowing us to collect the data and showing them here, and also the anonymous Tier 1 ISP for allowing us to show their data.
Think about frequency analysis of those routing events to actually find out, high oscillations and long oscillation. I don't know how, Fourier analysis or something. So you would get, breakdown into high oscillations, long oscillations, kind of, by algorithm.
Right. Yeah, we have thought about that. So you wouldn't want to know basically the crazy MET oscillation first, because it's flapping so frequently.
The components, I mean, if you see the whole time series, which is, sometimes difficult to grasp particular, components of it, especially if it is low intensity, high frequency, but it could be important, to the network health. I was just thinking.
Yeah. Thank you. Thank you.
Thank you.